So I just want to look at a couple examples. The next assignment is really nothing new. It's just using all the techniques of factoring polynomials that we've been practicing to solve some polynomial equations. So let's just look at some examples. And then I'm going to turn you loose if there's any time, and you can just start this assignment. Okay, so what about this one? What can I do here? Anything? Okay, so we could move the negative 243x to the left. What else? Any other alternatives? Okay, which one might be slightly preferable? So we get a positive leading coefficient then, right? So we'll push everything over to the right, and we'll get, let's see, what will we get? We'll get 768 x to the fifth minus 243x equals 0, but let's go and put the 0 on the right. We have that freedom, okay? Okay, good. What else? Those are big numbers, right? We want to see if we can factor something out, right? Yes, sir.
I'm pretty sure you can factor out like a 3x or maybe more than that too. I'm not sure.
Okay, I'm going to, you know what, I'm going to share something with you guys that I shared with my regular Algebra 2 class. Let me just pull this up. This is kind of cool. I don't think that's a perfect square. Don't think that's a perfect square. It jumps up from 524 up to 729. So that one's not. But it probably is. There probably is something we can do here, though. There's something in particular I really want to show you here. This one. Okay, let's go back. These are I've got some tricks here. Ooh, that looks weird. Let's change the background. There, that's better. Okay, there's some little divisibility rules. I'm just going to remind you, probably know most of these, but I want to remind you about these. These are good little tricks that you have for determining whether these numbers divide into a bigger number. The divisibility rule for 2 is obvious. Just if it's even, you can divide by 2, right? You know the rule for 3. I think we've talked about this. If the sum of the digits is divisible by 3, then the whole number is divisible by 3. Okay? And this will be in the notes, by the way. I'll publish the notes right after class, and it'll be available. And everyone knows where to find the notes on Google Classroom, instructional notes. Okay. The divisibility rule for 9 is the same as the rule for 3. If the sum of the digits is divisible by 9, then the entire number is divisible by 9. And what's cool about all these rules, too, well, at least most of these, and you can tell which ones, you'll know. You can apply these repeatedly. So, for example, if you had say you're dealing with some astronomical distances or something, and you've got these enormous numbers that have 28, 29 digits or something crazy like that, right? If you want to add those up and determine if the sum of the digits is divisible by 9, well, what if the sum of the digits is itself a pretty big number? You could do it again, right? You could take the sum of the digits and sum those digits and keep going until you get a manageably small number, and then ask yourself, is it divisible by 9? Does that make sense? So you can repeatedly apply these if you need to. Usually you don't have to do that. We don't typically deal with such enormous numbers that we have to do that kind of thing. But if you did, if you had a need, you could. So the divisibility rule for 5 is pretty obvious. If it ends in 0 or 5, it's divisible by 5. If it ends in 0, it's divisible by 10. That stuff, you guys already know all that. How about 6? Well, 6 is a combination of 2 and 3. If the sum of the digits is divisible by 3 and it's even, then it's divisible by 6, right? Everybody get that? Okay, how about 4? 4 goes evenly into 100, right? So you only have to look at the final two digits, because every digit after, like, I'll give you an example. Like if we take something like this here, if we take the number something like that, I don't have to consider any of these digits, because if I just look at the number 173290, 4 has to go into that, because this is equivalent to that many hundreds, right? It's 17,329 hundreds, and 4 goes into 100 evenly, so it has to go into that many hundreds. All you have to consider are the last two digits. If 4 divides evenly into the last two digits, it divides evenly into the entire number. Kind of cool. Okay, so it would divide into this one evenly, wouldn't it? Because 4 goes into 24 evenly. Okay, same kind of thing is true for 8. 8 doesn't divide evenly into 100, but it divides evenly into 1,000. So all you'd have to do for 8 is only consider the last 3-digit part. If 8 goes into the last 3-digit part, it goes into the entire big number. Okay? And then the weirdest one. This is a really, really bizarre one. The divisibility rule for 7. Let me pick a big number here, and I'll demonstrate this. This is pretty cool. Let's see here. Yeah, let's do that. Okay, we'll do that. We're going to try a really big one here. So for 7, let's try the number 162,498. So what do? You take the last digit of the number you're testing and you double it. So 8 times 2 is 16, right? And then I subtract that from the number created by the remaining digits. So the first step here would be I would get 16249 minus 16. Okay, and that's going to give me, I mean, this one's ridiculously big. This is going to take a while. Normally, you wouldn't be dealing with numbers this big. And then what am I getting here? 3. Okay. Well, I've still got a kind of a problem there. It's still too big to know, so we'll do it again. I'll take the last digit and double it, and I'll subtract it from those digits. So I'm going to get 1623 minus 6 gives me 1617. Okay. Still, is that right? Yeah. Got to do it again. That's going to give me 161 minus 14 is going to give me 147. Agreed? And then I can do it again. I get 14 minus 14 is 0. When you do that, if you end up with a number, and we could have stopped right here because we know 147 is divisible by 7. We could have just stopped there. When you do this trick, if the result is either 0 or a number that's divisible by 7, then the whole number is divisible by 7. How cool is that? That to me is just, that one is super cool, that it works, and it always works. It worked right here, but we just didn't know that number was divisible by 7, right? Does that make sense? Usually, how often do you deal with numbers that are that big, though, right? Usually it's a one-step process, but it always works. Questions on any of that? Okay, so I wanted to give you just a quick little number tutorial. Now let's look at these. See if we can figure out a number that divides into both of those. Two plus 4 plus 3 is 9. 7 plus 6 plus 8 is what, 21? So what's a number that divides into both of those then? 3. Okay, and then an x, right? Let's try that, and then we'll see if we can go any further. So this is equal to 3x times 3 goes into 7 twice with 1 left over. It goes into 16 5 times with 1 left over. That makes sense? So we get 256x to the 4th minus 3 goes into 24 8 times and into 3 once. Is that good? Pretty good with that? Okay. So now what? Now what? Does 256 look interesting? Yeah. It is. What do you get?
You get 16 squared.
Okay. So we could write this as a difference of squares, couldn't we? Okay. So 256x to the 4th. 256 is just 16 squared. It's a perfect square. So then this is going to equal 3x times the quantity 16x squared, right? Minus 9 squared. And how's that difference of squares pattern going to play out here? We can factor it as a difference of squares. Okay? What do we get? Three x. What's going to happen with this difference of squares here? Okay, so I get a squared minus b squared is a minus b times a plus b. Everybody good with that? Okay. Okay, now what? Okay, there is. But do I need to even use that? Because this time this is a different question than you were asked in the last unit, or not last unit, the last assignments. You were asked to factor completely. We're not asked to factor completely here. We're just asked to solve this thing. So can I solve these in a way that's easier than factoring? I can, right? Right. I can. What I would say, the way I talk about it, I can bail off the factoring train right now and just solve. There's no real motivation for me to factor this any further. Here's where I could apply the zero product property. How come? Because look, when I set these equal to 0, now I've got quadratic equations that are simple to solve. Right? Everybody get that? Okay. So we can just say, well, we get x equals 0, or if I set this equal to 0, I get the equation 16x squared minus 9 equals 0, right? Same thing as 16x squared equals 9, right? Divide by 16 and square root, and don't I just get x equals plus or minus 3/4 out of that? Everybody agree? Okay. And then what about this one? I'm going to get 16x squared. We'll write this whole process out for this one. 16x squared plus 9 equals 0. So 16x squared equals negative 9. So x squared equals negative 9/16. So what's x equal to? There you go. Plus or minus 3/4 I. Okay. So why did I pick that example? Because I wanted to illustrate that, we don't have to factor anymore after that, right? Once I get down to a quadratic factor, remember, we can solve by isolating for linear factors and quadratic factors, right? I'm always going to get both of the complex solutions if I just isolate x in a quadratic equation. Not true for a cubic. With a cubic, I have to factor it. Anything bigger than quadratic, I have to factor it. But with linear or quadratic, I can choose if I want to factor it or not. Okay? Thumbs up, thumbs down, thumbs sideways. How we doing? Okay? Okay? Well, let's get a few more. Let's try this guy. First step. Yeah, push everything to one side. Get it into standard form where it's set equal to 0, right? So we'll push everything to the left. If I push everything to the left, that's going to give me a 3x to the 8th, add to plus 105x to the 5th, plus 648x squared equals 0, right? Now what? GFC, good. What's our GFC here? Hearing it. 3x squared, good. So we can pull out a 3x squared. Which leaves us with, x to the 6th plus 35x cubed plus 216, right? Check my math. Does that look good? Okay. Now what? What am I going to do with that trinomial? Okay, true, but first I want to rewrite it in a way that looks better. That looks like a 6-degree polynomial, and it is. Okay, good. We want to write it in packets of x cubed so it looks like a quadratic trinomial, right? Good. So we get 3x squared times, we're going to pick some packets here so that we can get something squared plus 35 times something to the 1 plus 216. So it looks quadratic, and the something is x cubed, right? Okay, now that's good. Now we can go back to Unit 4 and we can just factor this with magic numbers like we would have previously. If they exist. Are there magic numbers that multiply to 216 and add to 35? Good question, huh? So let's make a table. Factors of 216. And they're both positive, right? Well, we know that 216, well, what do we know about 2? We know 3 goes into it. We could do 216 and 1, but obviously that's no good, right? And then if we look at the sum needs to be 35, so that's way too big. We got to get those numbers closer together. The closer the magic numbers get together, the smaller the sum. 24 and 9, there you go. Those add to, ooh, that's close, real close. It's supposed to add to 35, right? Yeah, that's close. We got to separate them. Just hopefully they exist. 8 and 27. There you go. Okay, there's our winner. Those add up to 35. Okay? If you're really, well, no, I don't want to get into that. Okay, so we got our magic numbers. So we're going to get, now this is going to factor into x cubed plus 27 times x cubed plus 8. Okay, now what? Can we just isolate the x's? I mean, if we isolate the x's by cube rooting, I'm only going to get the real 0 out of those cubics, right? So remember, our rule is if it's bigger than quadratic, the factors, we can't isolate. We have to factor. If we're looking for all complex zeros, which we are. We want all the complex solutions to this, including the imaginary ones. So what do? Sum of cubes. Those are both sum of cubes, aren't they? 27 is the same thing as 3 cubed and 8 is 2 cubed. So we can break those apart. Whoops, what am I doing? So we've got our 3x squared, and then we can split this up into make that a little bigger. We can break this up using our sum of cubes pattern. So see if you can tell me what that's going to be. What's the linear factor going to be for my sum of cubes in this case? Okay, good. So we're going to get x plus 3 times, good, plus 9. Very good. Okay, how did we get that? A cubed plus b cubed is a plus b times a squared minus ab plus b squared. Okay, good job. And then this one, we'd follow the same pattern, wouldn't we? Only this time, instead of 3's, we got 2's in there. So x plus 2 times x squared minus 2x plus 4, and that's all equal to 0. Okay, so we're essentially done. Now we just have to apply the zero product property. Well, our real zeros, we're going to get x equals 0, x equals negative 3, x equals negative 2. For these guys, these are irreducible quadratics, and how are we going to find those zeros? Yeah, go ahead. Well, there is, because what's the multiplicity of this 0? It's 2, right? It's 2 because this is being squared, the multiplicity equals 2. So it counts as 2. Okay? How am I going to find the zeros of these irreducible quadratic factors? Going to have to just use the quadratic formula, right? And I won't even, I mean, you guys, you've done that a million times. I won't even take you through that. You guys can do that stuff. Okay, one more. Looks terrible, right? So same as before, we're going to push everything to one side. We'll push it to the right side this time. So we get a positive leading coefficient. Okay? So that's going to give us, if I add 33, that's going to give me 32. X to the 5th. I'm going to add this 8x to the 4th. Going to add, oh, look at that. Those guys cancel, right? That's good. And then if I add the x squared, I'm going to get plus 108 x squared plus 31 is going to give me plus 27x equals 0. You guys check my math. Is that good? Good so far? Okay, what's next? Any GCFs I can take out? Take out an x. That's about it, isn't it? Okay. So we can take out an x. Whoops. Okay, now what? How are we going to deal with that 4-term polynomial factor? Grouping would be the only option. Is grouping going to work? Is it worth doing? You can tell me if it's going to work or not. Give me a thumbs up for yes, thumbs down for no. What do you think? Is grouping going to work? I'm seeing a thumbs up, another thumbs up, another thumbs up. Okay. How are you getting all those thumbs up? What's going on? I'm seeing thumbs up sprouting up all over the place here. Ah, there you go. Good. So look, if we look at the ratios here, the ratio of the first two coefficients, 32 over 8 equals 108 over 27. They're both 4, aren't they? So grouping has to work then. Has to work. All right, so let's group this thing. So then we end up with x, and inside the brackets here, in my first group, what am I doing? You talk me through it. I'll just shut up. You guys tell me what to do. 8x cubed. Okay, there's my GFC. And what's that leaving me with? Okay. Okay, good. So we have to have common binomial factors. So that's got to be a 4x plus 1, which means I've got to pull out a 27. There you go. Okay. So then what's this give me? X times... Okay, if I factor out the 4x minus 1, and then what's left behind if I factor out the 4x plus 1? Okay, good. Do I have to keep factoring? I do, because I've got a cube there. And this one is a sum of cubes, isn't it? This is just going to give me 2x quantity cubed plus 3 cubed. So what am I getting then? X times 4x plus 1 times A plus B. Okay, what's the next one? Ah, good, good. Not 2x squared, 4x squared, because I'm squaring 2x, aren't I? (6x). There you go, plus 9. And then I could just, I'm going to get linear factors from those three, and that irreducible quadratic is going to give me 2 imaginary complex conjugate zeros via the quadratic formula. Now, what if the question had been, find the real zeros? Then if I was only asked to find the real solutions to this, to discard any imaginary, then in that instance, does everybody see, in that one instance, I could have just set this equal to 0, and it would have worked, right? I just get x cubed equals negative 27/8. If I cube root both sides, I get x equals negative 3/2, which is what I get from this guy. Everybody see that? Okay. But if I'm trying to find all the zeros, I have to keep going. Okay, thumbs up, thumbs down, thumbs sideways. How we doing? Okay, I'm done. You guys can work.